All right, this is page 3 of note 17 of Calc AB. We're talking about the second fundamental theorem, which is something that you apply to accumulation functions. An accumulation function is a function that has a definite integral in it. When you have the definite integral in your accumulation function, the variable should be the upper bound, and the lower bound can be pretty much anything. So that lower bound will change the values of the function, but what it won't change is it won't change the derivative of the function. So it won't change like the rates of change and things like that. So let's actually use the second fundamental theorem and see if we can figure some of these out. So here we go. So it's all about identifying things. So here, the integrand is this, the upper bound is this, right? So the second fundamental theorem tells me that this derivative should be the integrand with the upper bound plugged in. So every t that I see in the integrand is going to become the upper bound, which in this case is just x. So it'll be e to the x squared times the derivative of the upper bound, which in this case is 1. So you wouldn't really write that usually, but we should write it. So let's see here. Let's identify. So we've got our integrand is e to the t squared. Our upper bound is x squared. So we're going to do the integrand, so it's e, with every t that we see replaced with the upper bound. So it's going to be the quantity x squared squared times the derivative of the upper bound. So times 2x. This I think I would probably write as 2x e to the x to the 4th, I guess. And then here, so this one, I'm telling you, second fundamental theorem like is the best. It's you don't have to find the integrand. Really, everybody knows the hard part about the fundamental theorem is actually figuring out the antiderivative. That's like working your way through that can be not that great. But second fundamental theorem doesn't matter. You don't need it. It's all about finding a derivative. Derivative is just inherently simpler. So this is going to be e to the upper bound squared, right? Every t becomes the upper bound, so it'll be sine of x squared squared. Ooh, too many not enough parentheses actually. Times the derivative of the upper bound. The derivative of sine of something is cosine of that thing. So messing up. Cosine of that thing times the derivative of that thing. Because we keep going with the chain rule. Like if you need the chain rule to find a derivative, you use it. So this is going to be 2x cosine of x squared, and then e to the sine squared of x squared. And that's your derivative, right? So it's not that bad. Like any day of the week, I would rather use the second fundamental theorem than the first fundamental theorem. It's just simpler. But both obviously have their places. So let's see what we can do here. Find the critical points of each function. Critical point in the domain of the function at which the derivative is 0 or undefined. So we're going to have to find the derivatives here. So let's see. So I'm going to call it dy dx is, all right, so it's going to be the integrand, which is sine of 2t. So I'm going to replace every t that I see there with 2x. So it's going to be 2 times 2x, and then times the derivative of the upper bound, which is 2. So this is 2 sine of 4x. Sine of 4x has a period of pi over 2. There are a lot of zeros of that. Oh my gosh. All right, so we're going 0 to 2 pi. So what's the easiest way to solve this? I don't really know. We could graph it. It's going to be like 4 full periods. I'm really just delaying as I decide like which of these not super great things I want to do. I'm just going to solve it. I'm going to say dy dx equals 0 would mean that sine of 4x equals 0. So that would mean that 4x could be equal to, so if x is between 0 and 2 pi, then 4x is between 0 and 8 pi, right? Just multiply through by 4. So I'm going to solve, so where does sine equal 0? Where does sine equal 0? So sine equals 0 at 0, I don't want to count that. Pi at 2 pi, at 3 pi, at 4 pi, at 5 pi, oh my gosh, at 6 pi, at 7 pi, but I don't want 8 pi because it's thankfully an open interval. So that means that x is pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, and 7 pi over 4. Okay, so those should be our critical points. Now, I think I'm going to check that on the calculator just to show you that we can do it. But first, I'm going to do the next one in case the calculator decides to destroy the video. Because if it does that, it usually only destroys the part where it comes in, and I don't want to redo the whole thing. So I'm going to check those in a minute. First, I'm going to try to do this one. So here, all right, so f prime of x, it's going to be the integrand, which is this, with the upper bound subbed in. So it's going to be the quantity 3, I guess, x squared minus 1 cubed. That's the integrand with the upper bound plugged in, times the derivative of the upper bound, which is 2x. Okay, so if f prime is going to be 0, then either x is 0 for sure, or what do we get? We got 3x squared minus 1 equals 0. So x squared equals 1/3. So x equals plus or minus, plus, what is it doing? It's like fixing all these things that don't need fixing. Okay, let's try that again. X is plus or minus radical 3 over 3. So these would be the critical points. All right, so we're just setting the derivative equal, just setting the derivative equal to 0. Or undefined, but the derivative, it's a polynomial, so it's never undefined. So I think that these are my solutions. So what I'm gonna do is I'm gonna check these. Maybe I'll check the everything on this page. Let's see how the calculator does with this. So I'm gonna share calculator page, and I'm gonna hope that it decides not to not work. So we'll see. All right. So I want the derivative. I'm gonna use templates hopefully. The derivative with respect to x of the integral. So you can just type it in like this, 0 to x, and then it's going to be e to the t squared, and then our variable is t. All right, so let's see what that derivative gives us. All right, so you're going to get warnings, like a lot of warnings when you do this, because the calculator knows it's doing dicey things. In my experience, these warnings never really apply all that often, but you should always think about it. So here we can make it x squared. Calculator knows what it's doing. So do we. We're getting them right. So let's change this to sine of x squared. And we get 2x cosine of x squared e to the sine of x squared squared. Nice. All right, now the next one that we're going to do. We're going to find, so I'm just going to continue on here. So we're going to find the derivative of 2x, and then this is not the integrand that we want. The integrand we want is sine of 2t dt. Let's set that equal to 0. Okay, and now let's try to solve. So menu 3, 1. I want to solve this equals 0 for x, but only on a certain interval. So let's tell it the interval. Let's go control equals. We'll do such that, and then 0 and control equals less than x, control equal, there's like a lot, and then 2 pi. All right, let's see. So pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, and 7 pi over 4. We got them. Nice. And then let's do this one last one. So these are all the problems that we did. Calculator can handle them, which is why you should always be checking on the calculator. And the more you use your calculator, the faster you'll be. My students always say that it's because I'm using the computer that I'm faster than them, which is true. But, oh, look at that. I forgot to even change the lower bound. The lower bound doesn't impact the derivative though, so it wasn't a problem, even though I forgot to change it. The real key to being faster is to have practiced a lot more. So even when I'm using a handheld, I'm still faster, and that's because I'm just constantly doing it. Oh my gosh. So this, can we factor this? Yeah, that's what we got. So we got 2x, that quantity, and then we wanted to solve when that equaled 0 for x. So we get plus or minus radical 3 over 3, and we get 0. We got them all. All right, so I'm going to go back to the notes, and I think I will call this a video here, and then come back in the next one and try to answer the rest of this page. So I will hopefully see you in the next video. So hope you're finding these helpful.